Hello, thank you for coming. I welcome all of you to Hello, thank you for coming. I welcome all of you to C++ Advanced Lecture 1. Hello,
brought by you
thank
by
you for coming.
the Code
I
to Universe
welcome all of
Foundation.
you to quick disclaimer.
C++
This
Advanced
is a
Lecture
free
1.
recording. Hello,
brought by you
thank
by
you for coming.
the Code
I
to
welcome
Universe
all of
Foundation,
you to
which means
disclaimer.
you can
This
pause
is
at
a
any
free
time
recording.
and
Hello,
you'll be able to
just
execute
welcome
encryption
all of you
when you're
to
ready,
quick
which means
disclaimer.
you can
So,
pause at
if
any
you need
time
time to think, if you
and
need
you'll be able to
something
encryption when you're ready, which means you
disclaimer.
can
So,
pause
if
any
you
question
need time to
just
think,
pause
if
and
you
ask the
need
question
to
something
encryption.
also,
Which
means
means
you
that
can
if
pause
you
any
should
question
have time to
and
think,
ask
and
the
able
question
to
something
also,
which means you can pause
if
and
you
ask
should
the
have time to
question
think,
and
and
ask the question something
first we are going to talk about value
which means you can pause
if
and
you should
ask
have
the
time to
question
think,
and
and
ask the
program is an expression.
something
First we are going to talk about value
which means
categories.
you can pause
If
and
you should
ask the
have time to
question
think,
and
and
ask the
program is an expression.
something
First we are going to talk about value
which means
categories.
you can pause
If
and
you should
ask the
have time to
question
think,
and
and
ask the
program is an expression.
something
First we are going to talk about value
which means
categories.
you can pause
If
and
you should
ask the
have time to
question
think,
and
and
ask the
program is an expression.
something
First we are going to talk about value
which means
categories.
you can pause
If Hello, thank you for coming. I welcome all of you to Advanced Lecture 1, brought by you by the Code to Universe Foundation. Quick disclaimer, this is a free recording. This whole system is YouTube Premiere, which means you can pause at any time and you'll be able to just continue watching when you're ready. So if you need time to think, if you need time to recap something, then just do that. If you have any question, you can just pause and ask the question in our Discord. Also, you should have the lecture notes while watching this, so you can pause and look something up there, and then ask a question, or then just continue. First, we are going to talk about value categories. Okay, in C++, the smallest unit of our program is an expression. An expression is a function call, something like a plus b, a minus b, a divided by b, a plus 1, etc. Each expression has a type. It can be void, double, or really anything, and a value category. That's what we are going to talk about. The standard defines GL values and R values in 6.10, which are further split into L values, X values, and PR values. You can see this graph here, which shows how expressions are categorized. So now, what does it mean? Well, historically, R values and L values are called such because they appeared on the left and right side of an assignment. So int I is the L value, equals 5 is the R value. Though that's not really helpful for us. Let's look at it a bit differently. So with something like this code shown here, so int a, b, c, a equals 5, b equals 2, c equals a plus b, b equals a. Now, what happens to 5 in the expression a equals 5? Well, it might be a weird question to ask, but does it exist beyond that expression? Is there like a 5 in our program just living on? Well, the answer is no. That 5 is a temporary value, and because it is of type int, it won't get destructed, but it will not necessarily get destroyed, but it will vanish basically after that expression is evaluated. The expression being a equals 5. Okay, so similarly, the expression c equals a plus b. Well, a plus b, now at this point a equals 5, b equals 2, so a plus b is 7 and c equals 7. What happens to a plus b? What is that? That is an expression by itself, a plus b, which is evaluated. But what happens to that 7 after it? Well, of course, it gets copied into c, but after that it vanishes. Like the 7, it was copied into c, but it doesn't exist anymore. These values which stop to exist are called R values. And like specifically a plus b, that is a PR value. So, what are common examples of R values? Well, first of all, literals, 5, 7, 6, anything. Results of most operators, like plus, minus, times, division, modulus, all things like that. And one thing which is really helpful in classifying R values is that we can think, can I take the address of this? This being the expression or the thing we are talking about. So, can I use the unary operator and, which when it is only one operand takes the address of something? Can I use that and apply it to something? Well, can I take the address of 5, just 5? No, I can't. That tells us 5 is an R value. Can I take the address of C? Yes, I can. C is an L value. Can I take the address of, in parentheses, a plus b? No, I can't. A plus b is a R value. That tells us to distinguish. But of course, there are operators which don't behave like that. For example, the indexing operator, the square brackets, which we use to index into an array, return an L value, because references are L values. Okay, so R value references. So far, we only had L value references, that is, references to normal variables. Now, we know that const L value references, like const int the reference sign I equals 4, that is a constant R value reference, and it can bind to an R value because it is const. We can print it, we can on an object apply any const member functions, but it is const, so it is limiting, and it doesn't tell us much about the nature of the value which we have assigned the const reference to. In the standard, there are two types of references actually, and the second one, which are R value references, are the ones of interest here. Okay, so R value references take the syntax of type and like the reference sign. My R value reference equals an R value. And R value references can only bind to R values. So doing something like int I equals 5, int R val reference j equals I is illegal, and it won't compile. So, what we can do is int reference symbol I equals 5, like shown here. And then we can actually change the value, so I equals 6. Now, one important thing, a really important thing to get is that R value references themselves are L values. We can take their address they exist beyond one expression. They are L values, but they can only be initialized as references to R values. Again, if you have any questions, please ask on YouTube or in the Discord. Okay, moving objects. So the nature of R values is that they are near the end of their lifetime. So for example, if we return a stud vector, it will get distracted in the next line, in quotes. Because actually in the program there is no such thing as a line, really, but it looks to us like on the next line in the actual code. Okay, we can leverage that knowledge. And the primary use of that knowledge is to optimize. Okay, so looking at this code for a dynamic byte array, we have stud byte, but I'm just gonna do using byte equals char, and then it's just some really basic code dealing with row pointers. We have resize, we have operator, index, and stuff like that. And okay, the code isn't that good, and you should use vector, but the point is not really how useful the code is, but to show an example, which is if you look at the copy constructor and at the assignment operator, that we always are copying stuff. We have to copy stuff. Now, let's have a function like range int max, like in Python you have the range. I think it's a function. I don't know much about Python, but pretty sure it's a function, not some kind of macro or language defined. Anyways, so range takes int maximum and then just behaves similarly to Python, and it returns that range. So if we in our main do something like int main auto x equals range 50, there it is copy constructed and data has to be copied. Well, to be fair, compilers probably will optimize this with RVO, return value optimization, but it's not smart to completely trust compilers to do stuff. That's not that good of a thing to do. So what we can do, we can overload the assignment and the copy construct operator, and then they're not copy assignment and copy construct, we call them move assignment and move construct. So what we do is we take an R value reference to the other dynamic byte array, and what we just do, we take their pointer, we take their size and null their size and make their pointer null. That means that on the next line, in quotes again, that DBA gets destructed and the destructor will call delete null ptr, which is perfectly fine. It will basically do nothing. So that's okay. But what we've done, we've just switched the pointers, or we really haven't switched it. We've taken that pointer, and yeah, so we have avoided copying stuff. And of course, this is just the constructor. If we had the assignment operator, we would have to delete our data before we do this. So the main takeaway is that by overloading functions to take R value references, we can optimize in the case that we get temporaries. And one thing to note is that R value references to trivially copyable types, that is int, float, long, char, and all of the basic types, basically, won't do anything. And the same is true for classes and structs, which whose only members are ints, longs, floats, and stuff like that. So you don't have to care about optimizing stuff with moving there. And just a quick note here, we call it moving because we haven't copied anything. We've just moved the data from one object into the other. Okay, std move. The STL provides us with a std move function, and technically we have to include the utility header to use it, but most standard headers already include utility for us, and std move is just such a universal thing which applies to basically any more complex class, so a not trivially destructible and copyable class. So it's not really looked down upon to just not include utility just because it is used so often. Anyways, one thing to get clear is that std move doesn't actually do anything. It just casts things. And specifically, it takes a reference to an L value. So for example, in this code here, we have a std vector of ints. We generate the data with the vector, and then we have a my object constructed from a vector, and we std move that vector. What that std move does, it takes a L value reference and it casts it to an R value reference. So that in the case that our object constructed from a vector is optimized, which in this instance we're just guessing that it is. So in the case that it is optimized for R values, basically we can just let it take all the data we want from the vector, use the vector however they want. They can move, maybe they have their own vector, which they use in that class, which then can be move constructed instead of being copy constructed. So std move basically just casts L value references to R value references, and the purpose of that is to, if we have some variable which we are done with, which we don't need anymore, we can so-called force a move, which means that we just do std move x, and that object is then the object is then usable because the standard specifies that standard library types which were moved from are in a valid but unspecified state. What does it mean? That means that all operations on that object which don't have any preconditions can be applied. So, for example, if we move a std vector, it's gonna be empty after we have moved it. So we can still do things like .empty, .size. We can do things like pushback, but we can't do things like pop back and access any index because the data just isn't there anymore. It has been moved. And note, and this is really important, never do return std move and the thing you want to return. Never do that. Because first of all, if you return something, it's already gonna be an R value, so you have nothing to gain. But second, you are preventing return value optimization, which basically is that the compiler will just use the object you've created in the function and just use that and don't copy anything, don't call any constructors. And it won't do that if you do std move on the return value. So you have nothing to gain but performance to lose. So don't do that. With all that stuff, we can have data types which can't be copied, but only moved. How? Well, the compiler only generates 4 functions if not supplied. Default constructor, copy constructor, copy assignment, and destructor. And if you just declare a move assignment and a move constructor, and we probably want a default constructor too, if you just declare that, it's not gonna generate the copy constructor methods, and then our object can't be copied. Although it's not a bad idea to just explicitly equals delete those functions just for the sake of being very explicit about what we want to do. And why would we want to do that? Well, there are data types like std unique pointer, which are supposed to be unique. So copying is a big no-no, and the only thing you can do to basically move your unique pointer around in your program is, well, to std move it. And the unique pointer is implemented such that after it is moved, it will point to null. So its internal pointer will be null pointer, and dereferencing it accordingly will get you a seg fault. Well, technically an undefined behavior, but it almost certainly will be a seg fault. In C++11 we got a new specifier, constexpr. We can apply constexpr to variables, functions, and memo functions. What is constexpr? Well, it means that our variable, function, or memo function can be a constant expression, but it doesn't necessarily have to be one. What are constant expressions? Well, constant expressions are evaluated at compile time. The standard doesn't say compile time, but that's basically what it means. So things like array sizes, template parameters, etc. are compile time only, and we need constant expressions to specify them. So we can also use constant expressions to have faster programs, because we can do calculations at compile time, which otherwise would have need to be done at runtime. The rules for constexpr initially were very restricted. So in constexpr functions in C++11, you can't do if, you can't do for, you can't do while, you basically can't do anything. But today they're far better, and we can even have constexpr classes. So for example, std array is constexpr qualified, and in C++20 we're gonna get a bunch of new stuff. It's gonna be the biggest release since C++11, and we will get stuff like constexpr std vector with dynamic allocations at compile time, which is crazy, but it is a thing, or it will be a thing. We can make most basic classes constexpr qualified too. And I highly recommend watching Jason Turner and Ben Dean's talk, constexpr all the things, where they build a JSON interpreter which interprets JSON at compile time, which is crazy too. And there's a link to that talk in the lecture notes. Constexpr variables. Okay, constexpr variables are mainly used the same way as just normal const variables, or hashtag defines in C. And one common example is for math, so constexpr auto pi equals 3.141, yada yada, constexpr auto e 2.718, constexpr auto sphere root of 2 1.41, and phi 1.618, and stuff like that. But they also can be used to store template parameters, to store sizes of arrays, and use them in such declarations. There are places where const can be used like that, but the rules are complicated, and it's generally just better to use const_expr. The only difference though is that const_expr variables have to be initialized with a constant expression. They can be literals, stuff like that, or if a type has a const_expr qualified constructor, we can have, for example, std_array, const_expr std_arrays too. Const_expr functions. Okay, so const_expr functions actually are not guaranteed to be evaluated at compile time if they are used normally. They are guaranteed to be evaluated at compile time though if you assign them to a const_expr variable, for example. And I'm just gonna quote Max Langhoff from Stack Overflow because he summed it up perfectly in a comment. Const_expr means there exist arguments to this function that may allow compile time evaluation. Does not mean this function will always be evaluated at compile time. This means, for example, std_apps can be const_expr. When called with const_expr arguments, it can be evaluated at compile time, but it can still be used as normal at runtime. So that is his comment, and it basically sums up all what you need to know. And like example uses, we can look at this code. We have enum class objects a, b, c, d, e, f, g, h. And if you remember, the number of permutations of a set number of objects is the number of objects factorial. So right below that we have const_expr auto factorial, unsigned in x, returns unsigned long. That at the end is called a trailing return type, and it's basically the same as if you'd put unsigned long instead of auto, but we're gonna learn about that too if you haven't yet. And it's just a basic factorial algorithm. And then in the int main we have a std_array objects 8, factorial 8. Now we want to store every permutation of those 8 objects. Is it better to put 40,320 in there or factorial 8? In my opinion, factorial 8 is clear the winner. It's much more clear, and we can reuse that function, and we can use it normally. It doesn't have to be in template arguments, so it's a clear win overall, in my opinion. And you could even do something like const_expr int object number equals 8, and then we could do shenanigans with templates and stuff to actually adapt this to be variable and compile time stuff with anything like this. So, and the next thing we could do is stuff like const_expr autopy equals math calculate pi 50. Given that calculate pi is const_expr, that will calculate at compile time the number of digits we need, and again, very flexible. And one of the most important things to know about const_expr functions is that undefined behavior will result in a compiler error. So you can't dereference null pointers in const_expr functions. So if you want to have a function and want to be sure there's no undefined behavior happening there, then you can just make it const_expr. And again, I advise you to see Jason Turner's const_expr all things and Bendine's, or just Jason Turner's C++ code smells and code tips. He has a lot of great talks, and he also has a podcast, cppcast.com. If const_expr, this is just a quick note, but we can do if const_expr like this, and the argument is a constant expression to that if, and we can use that to make compile time decisions on branching, like const_expr bool logging equals true, and then if const_expr logging stood cout my important info I want to log, or anything really. But we're gonna talk more about this in later lectures with templates and template metaprogramming and stuff like that. Okay, so that's it. Thanks all for attending. I'm sorry for the delay, and I just want to say that I didn't plan for this to come down like this. There's been a few complications and mostly personal failure too. And I hope the next lecture will be better than this. But still, thanks you all for attending. And see you next time. Don't forget to join our Discord. And yeah, for me it's almost 10 p.m. So I'll just wish you a good rest of your day.